So, okay, in this next video, what we're going to be doing is going over the Solow model. This model came out in the 50s. Solow got the Nobel Prize in economics. We'll go through the assumptions of his model, and we'll explain how depreciation fits into the model. And then we'll go and try to find the endogenous variables in this model, which are the steady state capital labor ratio and the steady state income per labor ratio. Okay, first the assumptions of this model. All the models have assumptions. So the first is it's a closed economy, so no trading. To make things simple. The second is no government or taxes. I mean, no government, which means no spending or taxes. So no G or T in this model. And the third assumption is that total factor productivity, the A term, is exogenous. And we're going to use a Cobb-Douglas production function. Okay, so we'll start off here with the Cobb-Douglas production function, which is y equals ak to the alpha, labor to the beta, where alpha and beta add up to 1, and alpha and beta are both greater than 0 and less than 1. And we're going to make a little change to it here. We're going to put in a time subscript. So a time subscript here on y, and a time subscript on k, and a time subscript on L. So by putting in the time subscript, we're making this a dynamic model that changes over time rather than a static model. Static models, we're comparing one equilibrium to another equilibrium, and a dynamic model is more of the path from one equilibrium to another equilibrium over time. Notice there's no T on total factor productivity, the A variable. And if we divide both sides by L sub T, and we're going to define YT over LT as little y t. So just like before, but with the time subscript. And KT over LT equals little k t. And then we can write this as little y t equals A times little k t to the alpha power. So very similar here. We just have now a time subscript on y and k. So if we graph this, we'll put YT over LT on the vertical axis, which is little yt, which is productivity. How much output is done by workers. And on the horizontal axis, we're going to have the capital labor ratio at time t. So little k sub t. And we can write this like before, where this productivity curve is equal to A times little k t to the alpha power. So like before, notice there's diminishing returns to little kt. And this line here shows there's diminishing returns. We're holding a constant. And in order to increase productivity, we'd have to either increase the capital labor ratio at time t, k sub t, or increase A. Now, what determines KT? Well, KT is endogenous in this model. Remember Malthus's model, there was labor and no capital. Looked kind of similar to this, but in this model, Solow is adding in capital. And he's doing it by having a capital labor ratio. So to increase productivity, we have to increase little k or A. And we want to figure out here, what should little kt be? Where would be an optimal or an equilibrium amount of capital labor ratio? Kind of like in the Solow model, we found an equilibrium. Well, how can we get an equilibrium in this model when we're adding in capital? So in the long run, equilibrium, savings at time t would be equal to investment at the time t. This will be the long run equilibrium. And we're going to say that savings is some function of income, like in Keynes's model. So savings at time t is going to be some function of income at time t. And we're going to write this that it's going to be equal to some fraction of income. So it's going to be equal to little s at time t, where little s is going to be equal to some fraction of income. It's exogenous. So something like 10%, 0.10. That would mean that people save 10% of their income. Okay, so similar to the Keynesian thinking here, that people, the more people make, the more they spend a certain percentage of their income, and they save the rest. Now, if we divide both of these sides here by L sub t, then we have S sub yt, little s. I'll make it a little bit smaller here. Little s sub yt equals investment. And we'll divide both of these by LT. Now, IT over LT is the amount of investment per worker. So IT over LT, we're going to set that equal to little I at time t, the investment per worker at time t. And we know that YT over LT is little yt. So we can write this as little s times little yt equals little I t. So the amount of savings per worker is equal to the investment per worker. And then we can write the investment per worker at time t is equal to S times A little kt to the alpha, since little yt equals A times little kt to the alpha. So now we've got savings equal to investment. Interest rate R is not in this model. The equilibrium is just where the amount of savings per worker equals the investment per worker. So let me go back up on this graph and draw the investment per worker. I'll draw that in red here. Little I sub t. Little sub I sub t is just some fraction of income per worker. So some fraction of this black line that's on there. So we can draw it as something like that. It'll be like 10% of whatever the black line is. So this is going to be income at time t, which equals little s times a little k t to the alpha. So we've got our income line in black, and then we've got the savings line, which is a percentage of that income, in red. Now we know that capital wears out. It's called depreciation. So capital wears out over time, or it becomes obsolete over time. And we're going to use little d, delta. Little delta is a symbol for depreciation. So we're going to say some fraction of the capital labor ratio wears out. So we can write this as delta times little k t is the amount of depreciation going on. Now let me draw this line up in the other graph here. Oops. Go up here. In this graph, I'm going to write or draw the delta little kt. And delta, the little d, is something like 5% or 10%, something like that. So it's going to be something like that, just a straight line. So this will be delta times little kt. That's the depreciation line. Now, a steady state in this model is the new amount of capital or investment that's being added to the economy is just equal to the amount that wears out. So the economy, the people are saving money, it's going into investment. And if that investment increases, the amount of capital is going to be increased. But the steady state is where the amount we add is just equal to what's been worn out through depreciation. And that's going to be right here where these two curves intersect. This will be little kt star for the steady state. So the steady state capital labor ratio is where the change in little kt is 0, where we're going to stay right there at that little kt star. And the change in little kt is going to be with a new amount investment at time t minus the depreciation is equal to 0. So right where those two lines cross is that steady state for the capital labor ratio. And if we go take a look here on the graph and say, well, what if we're not at that steady state? I'll draw this in blue. What if the amount of the capital labor ratio is up here? You know, put this little kt here in blue. Well, if we go up here to the graph, we can see what the savings amount is going to be, and hence the investment amount, because they got to be the same. But we can see the amount that is worn out is greater. So that means capital is wearing out at a faster rate than new capital is being put in. That means that the capital labor ratio is going to fall. There's going to be some capital dilution, and we're going to move this way towards little kt star. So there'll be some capital dilution here. On the other hand, what if the capital labor ratio is down here? Well, if we go up to the graph, we can see this amount wears out, but this is the amount that's saved. So we're saving more than is wearing out, which means some increases in the capital labor ratio, capital deepening. So we're going to move to the right here in the graph with some capital deepening. And we're going to be moving towards that steady state. Once we get to the steady state, then there's no reason for any capital dilution or capital deepening anymore. So that's why this kt star, right where the two curves cross, is a steady state level for the capital labor ratio in this model. Okay, so if kt is less than kt star, it means that savings and investment are greater than the depreciation, and the capital stock increases. And so we end up with capital deepening. On the other hand, if kt is greater than kt star, then the amount of depreciation is greater than the amount of new investment. So delta little kt is greater than the investment at time t, which means capital dilution. And both of them lead towards kt star, that stable equilibrium of the capital labor ratio. Now, what about output? Well, at the steady state, we should be able to read output off the graph. I'll put it in green here. At kt star, output is going to be right up here on this productivity curve. This is the output per worker, and that will be yt star. So you can see if we're not at equilibrium, the capital labor ratio is greater or less than the steady state, then income per worker is going to be greater or less than the steady state output. So this means once we get to this steady state, income per worker, really output per worker, is steady at yt star. And that means there's no growth in the economy. That means yt, which is output per person, stays there at that point. The only way we're going to have higher income per person is to increase the capital labor ratio, some capital deepening. But it's not going to be a steady state. If there is, and it's going to move back to the steady state, little kt star. The only way we're going to have higher output per person or worker, increasing the standard of living, is going to have to be here in A, which is exogenous. So what that means is, in this model, it's a model of growth, but in this model, growth is exogenous. The rate of growth here in the economy is determined by something outside the model in A, total factor productivity. When that changes, then if that increases, this black line shifts up and incomes rise and there's growth in the economy, but it's determined outside this model, not inside this model. So although this model is a model of growth, one of the first growth models, growth doesn't happen in this model. The growth is exogenous. Okay, so what we did here in this model, we went over the Solow growth model, went through its assumptions, explained what depreciation meant, and then we found these steady states for the model. And we'll end up with some sort of steady state level of capital per worker, and then some steady state of income per worker. And in this model, once we reach that steady state, then we're at the steady state income, and there's nothing that's going to change to increase income in this model unless something outside the model changes. And that something is total factor productivity. Okay. Solow doesn't explain what makes A change, why growth would happen. It's just exogenous, outside this model. Something else determines A and growth. Nothing in this model does, at least at the steady state, because at the steady state here, there is no growth unless A increases.